Hello, grade 12 chemistry students. This video will take you through PQ8, which is on the topic of the equilibrium constant expressions and calculations, as well as the reaction quotient, which is often given the shorthand Q. So let's begin with number one. Number one and number two are both conceptual questions involving forward and reverse reactions. So we are told in question number one, for the equilibrium of A plus 2B goes to 2C, the value of the equilibrium constant is 10. Well, that refers to the forward reaction. This is an equilibrium, so there's going to be a reverse reaction at play, but we always still consider the reaction going from left to right to be the forward reaction. And when we do the equilibrium constant, we're always doing the concentration of products over the concentration of reactants. So the products is always going to be on the right side, and the products is going to be on the right side, the reactants is going to be on the left side. So if we would consider the equilibrium constant for the reverse reaction, we would consider writing it this way, where 2C breaks down into A plus 2B, and then you'd go the concentration of products over reactants, and it'd be flipped over. So if the forward reaction has an equilibrium constant of 10, the reverse reaction, KEQ for the reverse, is always 1 over KEQ forward. It's just the flipped around thing. This is being flipped on its head. So you're just taking the inverse of that. So this would be 1 over 10, which is 0.1. Same logic applies to number 2. Okay, let's move on to number 3. What is the equilibrium concentration of bromine gas, or bromine liquid, I guess it is. It's technically a liquid. If the concentration of HBr is 0.35 and the concentration of hydrogen gas is 0.22 at equilibrium. So we're told the equilibrium constant is 62.5. So in general, KEQ is going to be the concentration of HBr squared over the concentration of H2 times the concentration of Br2, products over reactants, always. So we are looking to solve for this. So we know that the KEQ is 62.5. So I'm going to go 62.5. Concentration of HBr is 0.35, and that has to be squared over the concentration of H2, which is 0.22. And that would be times the concentration of Br2. So this is just a little solving for Br2. The concentration of Br2 is then 62.5. If we rearrange this, we're going to end up with 0.35 squared divided by 62.5 times 0.22. If we're rearranging it and using the algebra properly, and that works out to 1.44. Okay, if you're having trouble with the algebra here, please let me know, and I can help you out with more specific problems there. I am running off of the assumption that the algebra is not going to be the factor that determines whether you can do this problem or not. But if it is, please let me know and I can help you. So number 4 is a really similar question to number 5. It's just you're solving for a different unknown. So I'm going to let that one be. Moving on into number 5, here is a different style of equilibrium process. We are now told some information about the initial conditions. So we are told something about a reactant and a product, and we are given an equilibrium concentration, and we are asked to find the KEQ. So whenever you're doing equilibrium constant calculations, it has to be at equilibrium. It's the products over the reactants. This is at equilibrium. So in a question like this, we don't know all of the values at equilibrium. So we know a few things. We know that initially we had 0.5 moles of NaCl. It's in a 1 liter flask, so the concentration of NaCl is going to be 0.5 moles in 1 liter, so that's not going to change anything. It's going to be 0.15 molar. And the concentration of Cl2 is 0. Concentration of Cl2 is also 0.1 molar. Okay, so what do we know? We know initially that there is 0.50 molar of NaCl. We're not told anything about NO, and we're not told anything about Cl2 at the beginning. We are told something about the equilibrium of Cl2. So if there's no information given to you about initial conditions, there's no concentration of these. So this is before the reaction has been allowed to start. That has no concentration, and that has no concentration. Okay, what we do know is that we formed 0.10 moles of Cl2 when we measured it at equilibrium. Okay, so where did this come from? Well, it came from the no moles of Cl2 that were initially there. So we had a change of 0.1 molar Cl2 to give us the equilibrium value of 0.1 molar Cl2. But if Cl2 was formed, then NO also had to be formed by this breakdown of NaCl. But notice from the stoichiometry here that there's a 2NO and an invisible 1 in front of the Cl2. So if we formed 0.1 molar of chlorine gas, we had to form twice as much NO gas. So this is going to be 2 times 0.1 for a total of 0.2 molar at equilibrium. It's just 2 times as much based off of the stoichiometry. Now the same logic applies from going over to the reactant side of this. So we started with 0.5 molar of NaCl. Some of it broke down, not all of it, but some of it broke down. Because this also has a 2 coefficient, we can tell that the amount of moles of reactant that turn into product is going to be the same. So this is going to have lost 0.20 molar for a total at equilibrium of 0.30 molar. So now that we have all of our equilibrium values, we can plug it into our KEQ expression. So that will be the concentration of NO squared times the concentration of Cl2 over the concentration of NaCl also squared. So from here, it is a plug and chug expression. So NO is 0.20, and that's going to be squared. Concentration of Cl2 is 0.10. Concentration of NOCl is 0.30, and that is squared. You're going to plug that all into your calculator and do the exponents, and you should get 0.044 as the KEQ. So that tells us that this reaction is very reactant favored. It's a small KEQ, so most of the original product, original reactant has stayed in the reactant state. Okay, number six. So we are now told we have a 5-liter container and we are dealing with moles. So just be careful on ones like this that you are converting those into concentrations. We need concentration in order to get the key value. So we have 6 moles of SO2. So I'm going to go, we need to get the concentration of SO2. We need to get the concentration of NO2. We need to get the concentration of SO3. And these are all the initial concentrations. So I'm just going to put in here initially. So this is going to be 6 moles divided by 5 liters, and that will be 1.2 molar. This is going to be 2.5 moles divided by 5 liters, and that's going to be 0.5 molar. And this one is going to be 1 mole divided by 5 liters, and that'll be 0.2 molar. Okay, we are also told at equilibrium, so at equilibrium, that we have SO3's concentration at equilibrium will be 3 moles in 5 liters, and that will be 0.6 molar. Okay, so whenever we are given some initial concentrations and some equilibrium concentrations, we need to set up an ICE table. So we are going to set up our ICE table. We know that we have SO2 plus NO2 in equilibrium with SO3 and NO. So initial concentration of SO2 is 1.2 molar. Initial concentration of NO2, 0.5 molar. Initial concentration of SO3, 0.2 molar. Since we are not given anything about the NO, we are going to assume that it is 0. We are told that at equilibrium, this is 0.6 molar for SO3, and that's just coming right from there. So what do we know? So that means that the change in the concentration of SO3 must have been an increase of 0.4 molar. 0.6 minus 0.2 for a change of 0.4. Now that's important because that also means that there must have been 0.4 moles per liter of NO created. So this would be 0.4. And again, I'm just using the stoichiometry to do that. 1 molar here. Sorry, not 1 molar. 1 is the coefficient in front of the SO3. 1 is the coefficient in front of the NO. This equation is balanced with 1s in front of everything. So then, using that same logic of the stoichiometry, we know that we must have lost 0.4 molars of NO2 for 0.1 molar at equilibrium. We must have lost 0.4 molars of SO2 for 0.8 molar at equilibrium. And now we plug and chug that into our equilibrium expression. KEQ is going to equal the concentration of SO3 times the concentration of NO products divided by reactants SO2 and NO2. And then we have 0.6. That's coming from there. Here we have 0.4. That's coming from there. Divided by 0.8 and 0.1. Plug that into your calculator and you get 3.0 as the KEQ. So pretty close to 1. So this reaction would not be product favored or reactant favored. It is pretty balanced. Okay, number 7 is a similar problem to number 6. But instead of calculating the KEQ, we are now given the KEQ, and we are looking for an initial concentration of this SO3 gas. Okay, so at KEQ is 5 at a certain temperature for the reaction of 2SO2 plus O2, giving us 2SO3. A certain amount of SO3 was placed in a 2-liter reaction vessel. At equilibrium, the vessel contained 0.30 moles of O2. What concentration of SO3 was originally placed in the container? So we are looking for this right here. That's our X, the original concentration of SO3. We aren't told anything about the initial concentrations of SO2 or O2, so we're going to assume those to be nothing. And we had some amount of SO3 that started breaking down into O2 and SO2. We know at equilibrium that we had 0.3 moles of O2, so 0.3 moles of O2. Oh, sorry, I'm getting ahead of myself. You need to convert that to a concentration, which is done for you already here. Divide by 2 because it's a 2-liter vessel. 0.15 molar oxygen. So that means in the course of this reaction, we gained 0.15 molar of oxygen. Now, using the same reasoning as in the previous question, using the stoichiometry, we can see that we must have gained 2 times as much SO2 because SO2 and O2 are in a 2-to-1 relationship. So this is going to be 2 times 0.15 molar, which is 0.3 molar for an equilibrium concentration of 0.30 molar. Now, we don't know how much SO3 we started with, so we know that we lost some of it. Well, the amount of SO3 that we lost must be the same as the amount of SO2 that was gained because those coefficients are the same. So this is going to be minus 0.30 molar. For an equilibrium amount of some unknown, minus 0.3 molar. So that is kind of a typical setup of a problem such as this. So now when we put in our KEQ expression, KEQ is going to be the concentration of SO3 squared divided by the concentration of O2 times the concentration of SO2 squared. Now, we know that the KEQ is 5.0 as given. So the concentration of SO3 is going to be X minus 0.30 squared. O2 is 0.15 and SO2 squared is 0.30 squared. Okay, so a bit of algebra to do here, and again, if this is something that is you are finding challenging, and that's perfectly fine and normal to be challenged by algebra, please let me know, and I can help you with some of that math. So how are we going to go about this? I think the way to go about this is to do a little simplifying first. So this is a big, ugly denominator. So I'm just going to go here and say 5.0 equals x minus 0.3 squared. And I'm going to multiply out that denominator. So 0.15 times 0.3 squared is 0.0135 on the bottom. So that was this just simplified. Now I'm going to multiply by 0.0135 to cancel that out. Multiply this times 0.0135 and we get 0.067 5 equals x minus 0.30 squared. Now, instead of simplifying this out, because that would require the quadratic equation, if you have a square on one side and not a square on the other side, we're just going to take the square root to cancel this out. And then we're going to take the square root of the other side as well, because that's what we have to do. So the square root of 0.0675 is 0.26, and then that is going to cancel out this square and this square root. A square and a square root cancel each other out, so this is going to leave us x minus 0.30. We add 0.3 on this side and on this side, and we can see that we have x is equal to 0.56 molar. So that is how much SO3 we originally started with. All right, everybody, let's continue here on to number 8. So number 8 is based on the synthesis reaction of hydrogen gas and fluorine gas to make 2HF, which is hydrofluoric acid. We are told that there's a mole of hydrogen and a mole of fluorine, and these are sealed in a 1-liter flask at 150 degrees, which is not consequential to the problem, but anyways, and those are allowed to react. At equilibrium, 1.32 moles of hydrogen fluoride are present. Calculate the equilibrium constant using the ICE method. So we need to set up an ICE table here. So we're going to go ICE. We have H2 plus F2 in equilibrium with HF. So 1 mole of hydrogen and 1 mole of fluorine. This is a 1-liter flask, so 1 mole is going to be the same as 1 molar of each of these, and there's no HF to start. Nothing is mentioned, so that must be 0. We assume it to be 0. We are told at equilibrium that there are 1.32 moles of HF. So those all must have been formed after the reaction has started. So that makes the change of HF plus 1.32. Now, both H2 and F2 will have lost some of their concentration. I'm going to make sure that there's a 2 there. That is important. So that makes the change in fluorine, because the stoichiometry is a 1 to 2 relationship, there must have been half as much fluorine used in this reaction. So this is going to be negative 0.66. So that is the 1.32. That's divided by 2 for 1.66. Same reasoning here. 1.32 divided by 2 is going to make this a negative 0.66, and these are both in concentration molarity. So then, taking what we started with and what we finished with, that means at equilibrium there is 0.34 molar H2 and 0.34 molar F2. Now we can set up our KEQ expression, and that will be the concentration of HF squared over the concentration of F2 times H2, and that will be evaluated like this. Plug and chug, 15.1. Okay, moving on to number 9. Number 9, we are given a KEQ value for a similar reaction as number 8. Hydrogen and iodine makes HI. If we have 0.25 moles of H2 and 0.25 moles of I2, this is a 10-liter vessel, and they are allowed to react. What will be the concentration of each substance at equilibrium? Okay, so we're going to need an ice table here. We're also going to need to get some concentrations initially. So the concentration of H2 initially will be 0.250 moles divided by 10 liters. So 0.025 molar. Concentration of I2 is going to be the same, 0.250 moles divided by 10 liters, 0.025 molar. Okay, ice table. We have H2, we have I2 in equilibrium with hydrogen iodide 2. Okay, so we have 0.025 molar, 0.025 molar, no HI at the start, nothing is mentioned, assume it to be 0. Okay, and that is all we are told. So we don't know a lot of things here. We need to get these equilibrium values for all three of these in order to build our equilibrium expression. But we don't know how much H2 and how much I2 turned into HI, so these are just going to be some unknown amount. Okay, so we're going to be left with 0.025 minus x, 0.025 minus x, some amount. And when we go over to our products, again, looking at the coefficient, if we lost an amount x of H2 and I2, we will have gained twice as much product just based off of the stoichiometry. So the final amount of HI will be 2x. Okay, so here is how our equilibrium expression will work out. We have 49.5, and we are going to do products, 2x squared over reactants, which is 0.025 minus x, and 0.025 minus x. Now, something to realize here. Let me just rewrite this. We are multiplying 0.025 minus x times the same thing. So I can rewrite this as 0.025 minus x and put brackets around all of it and square it, right? Same number times itself is the same as squaring it. So that makes it a little bit easier mathematically to see. If I want to get rid of these squares, I can just square root the entire fraction and square root the other side as well to get rid of the squares. So the square root of 49.5 is 7.04, and then the right side is the same as it was minus the squares. And there we go. So from here, whoops, sorry, there's no square over here either. So now we can solve this by multiplying this over to that side. So 0.025 minus x times 7.04 gives us 0.176 minus 7.04x, right? The negative x times 7.04, and that all equals 2x. Now I want to isolate my x variable, so I'm going to add 7.04x and add 7.04x. So I got 0.176 equals 9.04x. Divide by 9.04, divide by 0, whoops, divide by 9.04. Final result, 0.019 is x. So what does that tell us? That told us the concentration. It gives us the value of x. So x was the change, going back to here, x was the change in our two reactants. So at equilibrium, part of my lack of space here, at equilibrium, the concentration of H2 is going to be 0.025 minus 0.019 for a total of 0.006 molar. And F2 is going to be the same. So I'm just going to do this and say F2 is equal to H2. And that is the same. And the concentration of HF is 2 times 0.019, which is 0.038 molar. And that is a lengthy question. I'm just going to pause this video for 1 second. All right, continuing on to number 10. Number 10, again, we are given a KEQ value, and we are told that we have 0.4 molar ammonia, NH3, and that's dissolved in water. And what are the equilibrium concentrations of NH4 plus and OH minus? So we are going to need an ice table again for this. So ice. Remember that water, in this case, it's just dissolving. So water's not included. It's a liquid, so it's not included in the equilibrium expression. So my ice table is only going to include ammonia, the ammonium ion, and the hydroxide ion. This is some acid-base chemistry happening here. You guys are going to learn a lot more about this in a coming unit. So what is happening here? So we were told that we had 0.4 molar ammonia and it's dissolved in water. And that's all we know. So we assume that there was no ammonium ion and no hydroxide ion. We lost some amount of ammonia. Now these are all in a 1-to-1 stoichiometry, so that must mean that we gained the same amount of those two products. So the change here is 0.4 minus x, or the equilibrium, sorry, would be 0.4 minus x, and this would be x. I'm going to get rid of the positive there. Just let me read. So that'll be x, and that'll be x. So now our KEQ expression, 1.8 times 10 to the negative 7, is equal to the concentration of the products. So that's going to be x times x over the reactants, 0.4, minus x. Now this can be simplified to x squared over 0.4 minus x. Now, if you have done some pre-calculus math, you might see here that when we multiply this out and go 1.8 times 10 to the negative 7 times 0.4, we get 7.2 times 10 to the negative 10 to the negative 8 minus 1.8 times 10 to the negative 7x, and that equals x squared. Now this is kind of setting up to turn into a problem that requires the quadratic equation to solve. If you have done anything like this in math, you know that an equation that has this form, ax squared plus bx plus c equals 0, and we could do that with this, right? If we take the negative x squared on each side, we'd have negative x squared minus 1.8 times 10 to the negative 7x plus 7.2 times 10 to the negative 8 equals 0, and then we have to do this big old quadratic equation. And I'm not even going to model that for you because it's not something that we need to do. Now, you're welcome to do the quadratic equation and solve for x and get the two values of x. One will be a negative and it will make sense, and one will be a positive and it will make sense, and you can get the accurate value, the 100% accurate value of x. But the expectation for this course is that you don't need to do that. Like I said, you're welcome to. So here's the thing. This is a very small KEQ. KEQ is a lot less than 1. So this is very reactant favored. What that means is that most of the ammonia is not being broken up into NH4 plus and OH minus. This value of x is going to be very small. So that initial concentration of ammonia, 0.4 molar, is going to still be there. Here's the equivalent. If you are lucky enough to be a millionaire or a billionaire, and you lose $1, it doesn't matter. You still are a millionaire or a billionaire. And that's the analogy for this. If we had 0.4 molar ammonia, it's a very, very reactant favored reaction based on the KEQ. So x is very, very small. This number is very, very, very small. So 0.4 minus x is going to be approximately equal to 0.4. It'd be like if we did 0.4 minus 0.000002, or whatever that number might work out to be. That's about the same as 0.4. That's going to be just a rounding error in the end. So what we can do is rewrite our equation here as 1.8 times 10 to the negative 7 equals x squared over 0.4. We assume that x is so small that 0.4 minus x is the same as 0.4. And now we can multiply this side by 0.4, and we can multiply this side by 0.4, and we get that 7.2 times 10 to the negative 8 is equal to x squared. Square root x is 2.6 times 10 to the negative 1, 2, 3, 4, 5 times 10 to the negative 5 is x. So, right, if you go, just to confirm what we did there, 0.4 minus 0.000026 is 0.3999974. So this approximation is totally fine. It saves you a whole bunch of work mathematically, and the result is not any different. Okay, so that was 11A. 11B is referring to the concept of the reaction quotient. So we went over that, or you should have gone through that in the notes. The reaction quotient Q Oh, sorry, what am I doing? I'm looking at the wrong thing. My apologies, guys. Forget this. I was looking at 11 and still working on number 10. So number 11 is a two-part question. So we asked our first to calculate KEQ, and then we are asked to calculate something involving the reaction quotient. So what the reaction quotient Q does is it tells us if a system is at equilibrium, and at equilibrium, Q is equal to KEQ. So we can see based off of the value of Q whether or not a system is going to shift left or right to be at equilibrium, or is it already at equilibrium. So this has two calculations to do. Okay, so let's start by calculating KEQ for this equation. So we're going to need some concentrations because we are given moles and liters. So we have 5 moles of CO2. So 5 moles of CO2 in a 2-liter container makes the CO2 2.5 molar. The concentration of CO is 0.2 divided by 2, which will be 0.1 molar, and the concentration of O2 will be, this one, I was reading this wrong. This one should be O2, and this one here will be CO, and that'll also be 2.5 molar. So let's calculate the KEQ. The KEQ is going to be the concentration of CO2 squared over the concentration of CO squared times the concentration of O2. Plug everything in and we get okay, so this is going to be, I'm realizing there's a small little error on my answer key that I need to fix. But anyways, continuing on with this, we're going to get 2.5 squared over 2.5 squared times 0.1. So these are going to essentially cancel out. We're going to be left with 1 over 0.1, which is 10. So the KEQ is 10 at equilibrium. So KEQ is at equilibrium. Okay, and then let's go down to B and calculate if this system is at equilibrium. So the value Q, the reaction quotient Q, can be calculated at any point. So here we're told that Q at any point has same setup here, 15.8 squared, okay, over 10 squared times 0.25. So Q ends up working out to 10 as well, or very close to 10, approximately 10. So that tells us since Q is very close to KEQ, this system is at equilibrium. And it's not going to shift one way or another. Okay, number 12 is a similar kind of problem. For the reaction of SO2 plus O2 gives us SO3, we are told initially that SO2 is 5 moles per liter, O2 is 10 moles per liter, SO3 has 0 moles per liter, and after 2 hours, the concentration of O2 is down to 7.9. Is this system at equilibrium? If not, which substances are increasing and which are decreasing? So we are given a KEQ value, so then we're going to calculate the Q value. So the Q value is using these values that are there at that state in time. So SO2 is going to be our product, and that is going to be squared. SO3 is our product, and that's going to be squared. SO2 is 0.8 squared times 7.9 for the O2. When you do the math here, you get a value of about 3 for the value of Q. And since Q is less than KEQ, this reaction will proceed towards the products. So is the system at equilibrium? No. If not, which substances are increasing and which are decreasing? So increasing will be the SO3 concentration, and decreasing will be the concentration of SO2 and O2. And there we go. That takes us through PQ8. Thank you very much.